Okay. All right. So let's do some more examples. So the first one I chose is an implicit differentiation problem. We have this equation that is not solved for y. There's x's and y's mixed together, and we want to find y prime. So the first step is to take the derivative of both sides. And when you do this, we're doing the derivative of both sides with respect to x. And we're treating y as if it's a function of x. So when it comes to taking the derivative of something like sine of y, it's like we're doing the chain rule. The outside function is sine. The derivative of sine is cosine. So the derivative of this is cosine y, but then we have to multiply by the derivative of the inside, which is y prime. The biggest mistake people make when they're doing implicit differentiation problems is they don't know where you put a y prime and where you don't. So this is an example of a place where you do put a y prime. Let's move on to this xy part. We're going to use the product rule here. And so the derivative of x is just 1 times y plus, and then now I'm to the part where the part of the product rule where I leave the x alone and I do the derivative of y. So that's another spot where a y prime comes in. And then for the derivative of this part, I'm going to have to use the chain rule. The outside function is this e, and we know that like the derivative of e to the x is itself, so there's going to be part of this that's just the same as above, but then I have to multiply by the derivative of the inside. For the derivative of this inside, again, I need the product rule. So the derivative of x squared is 2x, and then I get to the part where I'm going to leave the x squared alone, and I do the derivative of y cubed. When it comes to the derivative of y cubed, this is another spot where I'm doing the derivative of something involving y. It's a function of y. There's going to be a y prime involved, and so the derivative of what I'm doing is like the chain rule, where the outside function is the cube function. The derivative of the cube function is like this. And then you have to multiply by the derivative of the inside, which is y prime. And that's it. That's the derivative of everything we had on the left. And then we have to remember to also do the derivative on the right, which just gives me 0. Okay. Now it's just a matter of solving for y prime. And I see y prime in multiple places. There's one here, there's one here, there's one in here. So this is just going to be some algebra. The messiest part of this is this part, because I have this like inside this parentheses. I really don't like this because part of this has a y prime on it and the other part doesn't. And I don't like that at all. I can deal with that by just multiplying this all the way out. So that's what I'm going to do. The worst part of this is all the writing. So minus 2xy cubed e to the x squared y cubed minus 3x squared y prime e to the x squared y cubed. Like that. Okay. Now, again, let me underline all my y primes. There's one on here, there's one on here, there's one on here. These three things are going to stay together. Anything that I didn't underline, like this one and this one, are going to go over to the other side. And while I'm at it, okay, let me, I won't say too many things at once. For right now, I'm just going to write what's going to be on the right side. So on the right side, it was 0, but now I'm going to, like, these two things are going to have to move over. So I'm going to have a minus y and a plus 2xy cubed e to the x squared y cubed, like that. And what's going to be on the left? Well, these three things are going to still be on the left, but to save myself some time, let me write them with the y prime already pulled out, because I know I'm going to want to do that anyway. So with the y prime pulled out, I would have cosine y plus x minus this thing, 3x squared y squared e to the x squared y cubed, like that. And then finally, I solve for y prime. I just have to divide by this mess. So y prime is going to be this thing over this thing. I just have to write it. And that's it. Okay. Let's do one like this. So this one is, I didn't write it here, but this one should be logarithmic differentiation. On the test, if I give you one involving logarithmic differentiation, in the directions I'll say that I recommend that you use logarithmic differentiation. But this looks like it's kind of ripe for logarithmic differentiation, just because logarithmic differentiation is good for complicated fractions involving powers, especially when you have variables in the base and variables in the exponent. Like x is a variable, and I also have x's in the power. So what you do is you do the natural log of both sides. And because I don't want to write a lot, let me just write ditto marks, because all I did is the natural log of both sides. So natural log y equals the natural log of this stuff. And I don't even want to bother writing it, because the first thing I'm going to do is simplify it. So let me just write the simplified version. I'm going to simplify the natural log of this using log rules. And this can be done all in one step if you remember how this goes. Anything on the top corresponds to a positive logarithm. So for example, corresponding to this x plus 1 squared, I'm going to have a plus. I'm going to bring the 2 down, natural log of x plus 1. So it's the logarithm of this, and then this number is brought down. And then I'm going to have something similar for this. The sine x is brought down, and it's the natural log of this down here. Minus, because anything in the bottom becomes a minus, but other than that, it's the same. The 3 comes down, natural log of x squared plus 2. It's like that. Okay, now I'm going to do the derivative of both sides. And this step is similar, there's an aspect of this that is similar to implicit differentiation, which is the fact that on the left I'm doing the derivative of natural log y, and that derivative it's like I have to use the chain rule, so the outside function is natural log. The derivative of natural log is just 1 over the inside. But you have to multiply by the derivative of the inside. And that would equal, okay, now I have to do the derivative of this. So the derivative of 2 natural log of x plus 1. The 2 comes right down. The derivative of natural log x plus 1 is 1 over x plus 1 times the derivative of the inside, which is just 1. Plus, okay, here I have to use the product rule. So cosine x ln x plus sine x times 1 over x. Not so bad. Minus 3 times, okay, now I have to use the chain rule, 1 over x squared plus 2 times the derivative of this inside, which is 2x. Okay. Then right, okay. I'm going to be done in one step. I'm going to solve for y prime. That just means I'm going to move the y over. But instead of just writing the letter y, I'm going to write what y is. So I'm going to write all of this. So x plus 1 squared, x to the sine x, over x squared plus 2 cubed. That's y, and it's times all of this. And I'll just clean it up a little bit as I go. Okay, 2 over x plus 1 plus cosine x ln x plus sine x over x minus 6x over x squared plus 2. That's it. Okay. Let's do one where there's a function and an interval and you want to find absolute max and min values. If you remember, these are the ones where you find the critical numbers. That means you take the derivative and you set it equal to 0 and see where it's undefined. And then in the end, you plug in the endpoints of the interval to the original function, and you also plug in any critical points in the interval into the function. The biggest is the max, the smallest is the min. So the first step is to take a derivative. And actually, right. Let me, because right. I don't want to take too much time doing this, but I'll rewrite f this way. Like instead of 4 over x minus 2, it's 4 times x minus 2 to the minus 1. This is just easier. I can always use the quotient rule here, but I don't really like the quotient rule. This is going to be easier. So if I take the derivative, I'll get 1 plus 4 times, now I'll just do the chain rule, negative 1 x minus 2 to the negative 2 times the derivative of the inside, which is just 1. And I'm going to need to work with this. I'm going to need to solve an equation with this, so let me clean it up. 1 minus, and then, let's see, this would become an x minus 2 squared on the bottom, so 4 over x minus 2 squared. All right. So this is the derivative. The first thing I usually check is if it's undefined. It would be undefined, of course, at x equals 2. There's really a couple of reasons why we're going to ignore that, though. First of all, the original function is also undefined at x equals 2. So that would be one reason to ignore it. Also, the interval in question does not include x equals 2. So we're going to ignore this one. But anyway, we checked where it's undefined. We just didn't find anything relevant. We should also check where it's 0. So I'm setting this equal to 0. So I'll get this over. So 1 equals 4 over x minus 2 squared. I'll multiply this over. So it should be a little bit more organized, but x minus 2 squared equals 4. I'll do the square root. X minus 2 equals plus or minus 2. So x is 2 plus or minus 2. So 0 or 4. Okay, and if I'm being careful, we should only pay attention to anything that's actually in our interval. So this one is not relevant. So really the only thing we found is 4. So yeah, maybe I should have left myself a little bit more room here, but I'll be fine. Whoops, I don't need f of 0. I need f of, okay, once again, what am I doing? I'm plugging in the endpoints, and I'm plugging in any critical points that I found, at least the relevant ones. So the only one of those is 4. So in other words, I need f of 3, f of 4, and f of 5. F of 3, and it's important, we're talking about the original function here. So f of 3 would be 3 plus 4 over 1, so 7. F of 4 is 4 plus 4 over 2, which is 6. And f of 5 is 5 plus 4/3, which is 19/3. And just because I'm going to need to compare this to other numbers, 3 goes into 19 6 times, so that's 6 1/3. I'm just doing that because I need to know which of these numbers is the biggest and which one's the smallest. So then it looks like this one's the biggest, and this one's the smallest. And I have just enough room to make a little bubble and draw my final conclusion. Absolute max of 7 at x equals 3. That's that number and that number. Absolute min of this number at the value of x that achieved that, which was x equals 4. All right. Yeah, so maybe let me stop this video and start a new one.